Moving on, we have our second tech talk. It's based on cost optimization of systems in enterprises, which is crucial with quality and performance awareness. We will delve deeper into this with the talk titled Optimizing Costs, Quality and Performance One Algo at a Time by Koyel Mukherjee, Senior Research Scientist, Adobe. Koyel Mukherjee is a Senior Research Scientist in Adobe Research, Bangalore. Her current interests are in the areas of efficient generative AI through algorithmic and learning-based approaches. Earlier, she has studied several cost optimization problems in enterprise systems, such as storage costs in cloud and data redundancy in data lakes. She publishes in top CS conferences such as ICDE, SIGMOD, ICML, etc. Prior to Adobe, she has been a part of Xerox Research as well, and has also been a part of IBM Research, Bangalore. Let's welcome Koyel Mukherjee with a round of applause.
Am I audible? Okay, yeah, so thanks for the kind introduction. Am I the only one standing between you and lunch? Okay. Not a very enviable position to be in, but let's see what can I do. Let me also get some exercise walking through the room, because I feel like this side of the room is sort of, not getting a lot of focus. So yeah. Thank you. Okay, yeah, so my talk is on basically algorithms, optimizing costs, quality, and performance using several algorithms. So I'm currently a senior researcher in Adobe Research. And so algorithms are my first love. That's what I got my PhD in from Maryland, long time back. Please don't ask me when. So yeah, and but since then I've moved on to machine learning and deep learning, and off late Gen AI, right? Everyone has to jump onto that bandwagon. Otherwise, you've not arrived, right, Aruna? Right. So yeah, so this talk I'll mostly focus on I'll mostly focus on one of the papers that we recently presented in ICD, which will be mostly an algorithms and machine learning based work. But to start with, I'll first give an overview of some of the works and problems that we are solving at Adobe Research. I mean, this is actually only a partial view, because this gives you a flavor of the systems and insights work that's going on. But there is a lot of work, as you know, in Adobe on PDF side, document experiences, and text-to-image models. Adobe Firefly is, of course, a really great product. And if you haven't tried it, I totally encourage you to go and try it out. So yeah. So as I said, I mean, my focus has been on reducing costs or operational expenses while maintaining a certain quality standard, or even improving the perceived quality, performance, and customer experiences. So some of the works that we have done along these lines are, one is on the storage cost reduction, which will be the focus of my talk in this in this session, which is the first one. So I'll not spend much time on that now. The other interesting work that we did along these lines was, so you might not be aware, Adobe also has this data management platform, where we are hosting the data of lots of customers, big customers. And we often run into several challenges as to how to manage that data at scale. And often there is a lot of redundancy in that data. And how do we somehow maintain data hygiene, minimize the data in the data lake, not only for reducing the storage costs, but also for optimizing the performance that customers see, and also say for privacy compliance reasons, as well as for compute cost reduction. So this work is also currently published, and you could look that up. And yeah, who can escape Gen AI, right? So some of the works that we've recently been doing, they are on the generative model side. But again, my focus is how do we optimize the costs while keeping or improving the performance, either keeping the performance same or improving the performance. So yeah, we approach it in different ways. This is also on archive, currently in submission, but it's also on archive. You can go and take a look. So some of the things that we explore in this work include, so if you have a stack of LLMs, even OpenAI has a stack of LLMs, right? There's GPT-4 Turbo, there's GPT 3.5, there was Text DaVinci and Curie and so on. Now, do you need to use the heaviest hammer for every task that you have? And is the heaviest hammer going to give you the best performance for every task? So that is those are some of the questions we explore in this. We try to estimate which models are good for which task, and can we sort of optimize their usage in an intelligent manner so that the overall costs go down, latency thresholds are met, as well as the performance not only remains the same, actually even improves, as we show in some of our results. And also on the prompt optimization side, so there was a talk right before this, right, where a lot of it was on prompt optimization. But again, we look at it from the point of reducing the costs while maintaining the quality for any desired tasks. So now getting to the main tech talk part of it. So this was a paper that we presented last year in ICD. This was on optimizing storage costs on the cloud. So now why is this an important problem, and why did we want to study it? So cloud costs are really spiraling for most organizations across the world. And this is because of this huge amount of data that is being generated. There's this clickstream events and a lot of other analytics data that's piling up every day. And this is not only increasing the storage costs, but also compute as well as processing. And as you can see from this infographic from ICD, this annual size of the global data sphere is exploding. And optimizing this spend is often a big initiative in many organizations. But this is not a trivial problem. One of the main things is, so the cloud storage that we avail from providers such as, say, AWS or Azure, that comes in this multi-tiered format, where you have these different tiers of storage, each coming with its own characteristics. As in, you can see from here that the storage cost is decreasing exponentially as we go from the premium to the archive layers, whereas the read cost is increasing in the opposite direction, again in an exponential manner. So, and also the latency varies between the tiers. So how do we make a sort of an optimal decision? Where do we want to put our data while minimizing the cost and latency, meeting latency thresholds and everything? To top it all, there is this varying access patterns of data that we often see in enterprises. So here are two charts that I'm showing, which we actually analyzed from our data in the data lake. And we, in fact, see that only like 6 to 7% of the data account for more than 80% of all the customer accesses. And all of the other data is just lying there. But we do not analyze all of this, and we put everything in the premium and hot tier because we do not want to, violate SLOs or something like that. Again, more than 80% of data sets have 0 accesses from customers over a certain period of time that we analyzed. Also, the access frequency often decreases with age. So this brings several key issues that we wanted to address in this work. One is the cloud tier, where you want to store the data. That has to be optimized. And rule-based policies often fail because there can be certain seasonality in your data access, certain periodicity. So if you just have a rule that if my data is not accessed for 30 days, let me push it to the cool tier. What if your data is accessed every 3 months for, say, quarterly review or something, right? Then you're continuously thrashing the data between the cool and the hot tier and paying actually much more. Moreover, there's another interesting angle. So within the same data set, and which might even range to terabytes, it is not that all parts of the data are equally important or equally frequently accessed. It is that we find that some parts of the data are more important or heavily accessed than others. Now, this can be temporal. It can be that it's most recent files in the same data set. but it might be something else as well. Maybe it is some more important users' data or something which might result in this kind of a access pattern. So whatever we do, this positioning of the data in the storage tiers, we also have to be aware of the workload or access patterns. Now, you can tell me that why not just compress the data, and this will just reduce the cost. But you also have to keep in mind that this will add the overhead of decompression, which can increase both the latency as well as your compute cost. So clearly, it's, and how do you even know which compression algorithm will perform optimally for which type of data? That brings in another angle of complication. So in this work, we tried to come up with some non-imaginative names for the different problems that we studied. And here are they. So Optassign is, now given that we have a predicted volume of accesses for our data sets for a given period, can we determine the optimal assignment of tier and compression schemes while we maintain all the latency and storage capacity requirements? The second is, to solve the first one, we first need to know how the compression algorithms will behave on each type of data. So the second problem is trying to predict or estimate the compression ratio as well as the decompression time that each compression algorithm will take on different types of data. The third is the partitioning, the workload-aware partitioning angle that I was just mentioning. So we want to do a workload or access pattern aware, optimal and efficient partitioning of the data. And finally, we put all of these things together in this unified pipeline that we call scope, storage cost optimization with performance guarantee. Then these were some of the data sets that we used in this work. So some of it is enterprise data. In some cases, we have access to all of the data, but that volume is small. In some cases, we have access to only the metadata, and that volume is large. So we had to see what we can do only at metadata level. And we also have this open source data, which is TPCH data, which is frequently used in this kind of analysis. This data had like different skews and different access patterns as well. Okay, so coming to Optassign. Hope that slide is impressive. So this is trying to determine the optimal assignment of tier and compression schemes, given that we know this is the access pattern and these are the performances of the compression algorithm. Suppose we know it all. Can we still optimize the tier and the compression scheme for given sets of data? Turns out that's a hard problem. That's NP hard. And this linear program or integer linear program is trying to capture all the different aspects of this problem. Now, I'm not going to try to bore you with all of these details, which you can obviously find in the paper and fall asleep. But what I'm just trying to give you an idea is that this is trying to minimize different types of costs. This big objective function at the top, it's trying to look into storage costs, the read costs, the write costs of the data based on this access patterns. And the constraints below are trying to make sure that certain constraints are satisfied, such as if you have a certain limitation that in a certain tier, you can only use up to so many terabytes, then you do not want to exceed that if that is your agreement with a service provider. So that is one constraint. If you have certain latency bounds, as in maybe your service level agreements with a particularly premium customer does not allow you to have any slack on that data, then for that you'll probably have to end up paying high and have to satisfy those latency constraints. So those are some of the things that this particular ILP is trying to capture here. Now, okay. Yeah, so that is a hard problem, but part of my research and some the thing that I like doing is, for a hard problem, can we find a simpler solution? Maybe by simplifying the problem slightly, maybe relaxing certain assumptions, maybe relaxing certain constraints, and seeing if that is a relevant problem also for the industry, for our particular enterprise. So here are two particular cases that we solved, for which we showed that you can actually solve them with efficient polynomial time algorithms for these cases. The first one is, if you have equal size data partitions, and no compression that you want to apply on them. Then you can actually model it as a bipartite graph and solve it using Hungarian algorithm, which looks into finding the minimum weighted matching on that bipartite graph. Now, you might say, why is this an important case? Now, there might be certain size constraints that your system administrator has imposed on the ingest pipelines, because of which your data will be ingested in certain equal size chunks. And therefore, this actually also becomes an important problem for enterprise to solve, and we can solve it pretty easily. Details, again, I'm going to skip because I know lunch is waiting. So, yeah. All right. The next simple case that we considered, which is actually the solution that became very important for us, is when there are no fixed capacity constraints. So I mentioned something like, what if in a particular tier, we can only go up to certain terabytes. But in most cases, such kind of restrictions often do not exist. It's like use as much and then you pay for it, right? So actually, there is no storage capacity. It is infinite. So if that is the case, keeping all other things like compression, unequal size partitions, everything, a simple greedy algorithm, which actually give you the optimal solution. We show this provably. It can be evaluated very fast in linear time, and this is what we ended up applying to our problem. So here are some of these results that we got with this greedy algorithm. So here we projected the access patterns for 6 months using historical access logs. And we show that there's like such a huge scope. I mean, that is the name of a pipeline, but I like to advertise it as much as I can. So yeah, there's a huge scope for optimizing the costs here. You can see that the cost savings are can even reach like more than 80% for certain customers. But the previous one assumed that the access patterns are sort of known, offline analysis. But what if you don't know the access patterns? So there, we were able to come up with this strategy where we can use our offline optimal algorithm as well as a machine learning model. In this case, we use random forest. I'm sure XGBoost will also do equally well for this purpose, where we actually annotated some of the data. Basically, we had some data already, access logs. We broke it into some training data, validation data, test data. Using the training data, we solved opt-assign and came up with our annotations for this different, okay, this should go to hot, this should go to cool, so on. And used that as training data to train our random forest model, validated it on the next 2 months data, and then using that as the signal for the next 2 months data, which was a test data, we evaluated the performance. And the features that we used were size of the data, months since creation, aggregated accesses, and so on. So, but the point is, using this model, we were able to achieve a very good prediction accuracy, as you can see from this confusion matrices, and we're able to come up with pretty large savings, even when the data is unseen. Now, so far we assumed this compression performance is known, and historical access patterns, okay, we already addressed that, but what about compression performances? That is also unknown at runtime. So for that, again, we came up with another model, again, random forest-based model, which was able to estimate the compression ratio and the decompression time that each compression algorithm that we had in our stack, it would achieve on different data partitions that we had in our training set and test set. So again, this was able to achieve pretty good performance for these several different algorithms that we tried. We proposed this weighted entropy features for doing this. Now, finally, coming to this orthogonal part, where we want to do this workload or access-aware data partitioning. So far, it's like we have looked at the data set as a one single entity, and we decided whether to put it in hot tier, cool tier, what compression algorithms to put into. But should we consider the whole data set? As I said, right, certain parts of the data set might be more important than other parts. So in that case, we wanted to solve this problem where if we could come up with an optimal set of partitions which will minimize the storage space that they take, but at the same time also keep the total read costs for this data under a certain bound, because compute is often more, what can I say, the pain point for enterprises, even more than storage. So compute was sort of the hard bound for the read costs, and we wanted to minimize the storage space. So this is what we did. Suppose you have this query logs, and we came up with this query families where we sort of abstract away the different columns, and we just look at the rows. Think of tabular data sets, right? That each access is reading. Now, based on these initial accesses, we come up with certain initial partitions or chunks. Say F1, F2, F3, F4 to F7 are these chunks. Now, there would often be a lot of overlap, again, between these chunks. So while the size of each individual chunk is small, and you can, say, read them fast, the read cost is sort of getting low, but your storage cost is again increasing. So it's a trade-off, right? Because you're now storing a lot of duplicate overlapping data. So can we merge some of these partitions optimally? Again, optimally because this is trade-off. So that overall storage cost is going down, whereas while keeping the whole read cost, expected read cost under a certain bound. So that was the main purpose of this particular piece of work. Again, this turned out to be a hard problem. This is again NP hard. So here we were not able to come up with a provably optimal algorithm, but we were able to come up with a very practical and efficient heuristic algorithm based on modeling it as a graph, which worked very well. So what we did was, so think of these data partitions as these nodes of a graph. For example, U1, U3, UT, U2, U4, the initial nodes. Now, edges will exist between every pair of these nodes, and the weight of this edge would be the fractional overlap between these data partitions. Now, the idea is, can we merge some of these nodes to come up with this kind of a resultant graph so that the overall space, as I mentioned, is minimized while the compute is under a bound. So how we solve it is using a max heap based algorithm after doing this kind of a graph-based modeling, where we the max heap is on the fractional overlap or the weight of the edges. First, we'll pick greedily the weight which will give us sort of the maximum benefit of merging, and we sort of continue this iteratively. So every time we pick an edge, what we're doing is we are collapsing the two nodes to form a bigger node, which will become the merged partition. And we will be removing that edge from the heap, and there will be new edges generated in the heap, and some edges will be deleted, so there'll be again heapify, and we will repeat this till we are left with certain singletons, and which we will just pass as is to our data set of partitions, because it is clearly not feasible to merge them. Okay, so I'm really out of time. Now, these two figures show that this particular heuristic was able to achieve a pretty good trade-off between the duplication or the overlap that we got and the cost of merging, which was the read cost increase that would have. And for, again, a simple case where we have certain ordering between the partitions, which can be the case if there is some sort of a temporal nature to these partitions, we were able to come up with a dynamic program which is sort of a bi-criteria approximation to this. If S opt is your storage cost and C opt is your total read cost, then our solution would be 1-2 approximation, as in we would be within the optimal cost, but we would be within at most twice the read cost of this. And this is the final thing where we put everything together, the final pipeline, and it was able to beat closest baselines by pretty good margins. So we didn't find a baseline which solves exact same problem in the literature, but we were able to modify existing baselines to sort of conform to our setting of the problem and show the performance. Interestingly, what we found is this G-part, or the graph-based partitioning algorithm that I just talked about. If we apply it with the baselines as well, their performance also improves. So that itself is also a significant contribution. So yeah, so this work, we show that this works across different types and scales of data and gives cost benefits often 50% or more. So yeah, I would like to end my talk here, and these were the references that we referred. And I would be happy to take questions in the 2-minute, 36 seconds that we have. Yeah.
So, hi, I'm Renuka. I'm from Pure Storage. So, one of the data centers, we manufacture data centers, right?
Right.
So,
You're going to catch me.
no. So, this is a very interesting problem because many people are not aware of the tiering system. I mean, maybe they're aware, but they're aware only after incurring additional costs, which they wouldn't have expected, right? So, for a firm like ours, which manufactures data storage and data centers, we would want people to not be aware, right?
Okay. Yeah, as I said, you're going to catch me. Yeah, let's take a fight outside.
No, no. The point I was trying to make was how do we still, make it profitable for everyone, like despite us profiting from more data usage? How do we collaborate better with algorithms like this, make it more public and, make it mutually beneficial? Eventually the usage is going to increase, right? In a more optimized manner once we collaborate. So what are your ideas and thoughts?
Right. So, by no means I'm an expert on that, but what I can say is, so this scope or opportunity to optimize the costs arose because the pricing of the tiers, is done in a sort of agnostic manner to the data access patterns of the particular organization, and we were able to sort of exploit that in this work to come up with a reduction in cost. Now, a good or a mutual sort of common ground can be if the data or cloud service provider as well as the enterprise sort of come together and come up with sort of a customized pricing plan based on the expected access patterns for that enterprise across different customers. I mean, this is something that I can suggest. Seems to be worked out. Fight is outside. Yeah. Other questions?
Yeah,
Yeah.
we have
Hi,
one here.
myself Sohini. I think this topic was very close to me because we are working on the, cost compute part of it. So I see your algorithm was mostly on the computing cost post the data. It's been there on the data sets, right?
Yes.
So is there a way that we can enhance? So once if I'm a user, I want to create a data set. As a user, as an engineer, I wouldn't really, think beyond what could be the cost. So as a proactive measure, when just I want to create a data set, so the algorithm reads it and just suggests me. So this could be an ideal approach to, have the right sizing or a right computing. So that could be as a, as a proactive measure than the reactive, then, spending the cost and then bring it down. So as an operational engineer, I would say just cut on in the initial stages of the creation.
Right. That's a great question. And we did not address it at all in this work. Here we assumed that the data sets are already there and what can we do about that problem. But what you're suggesting is a great, I would say, sort of future work to look at, where you can, so if you're looking at it from the customer point of view, or are you looking at it from like the enterprise who's providing the data management? So because the data sets are often created by customers, right? So we often don't have any handle there. What can we do there? So
yeah, from the engineer perspective, so from the company's perspective as well.
which company, data management provider or the customer who's availing of the data management?
From the data, customer provider, yeah.
From the customer perspective, right? So yeah, so here there's also an interesting angle here. Often this cost is abstracted to the customers. So yeah, but suppose the customer was also in the common ground and we are trying to optimize the cost, then I would think that maybe looking into the historical access patterns, right? And what sort of data is, say, used more and what sort of data is used less. We could maybe already come up with sort of a proactive partitioning of the data so that the data can already be ingested in certain tiers using that information. For example, some data maybe can go into cool tier because you are not likely to use it, say, every you're likely to use it only every 6 months or so, right? On the other hand, there is some data you'll be probably accessing every day, and that data, if you're aware of when you're ingesting at that time itself, we could ingest it into hot tier, and that can be beneficial to both customers as well as data providers. Yeah.
Thank you.
We can take a few more questions. We have time for that. Anyone? All right. We would like to give you a token of appreciation. We have Samyak Rajnala. He's our senior data scientist at Intuit. He's also called the stats guy with the Stanford PhD internally.
Oh, okay. Thanks. Thanks. Thanks, everyone. Thanks for your patience before lunch. Yeah.
Thank you so much, ma'am. Next, we'll be breaking for lunch. It's going to be almost an hour long. So there's also the right time to connect with other attendees, find your potential collaborators, and share and spread ideas. We'll be back here in the same room in an hour's time. We also have Kahoot quiz. They're one